Hello dear students, this is Dr. Vijaya Babu. So in continuation with the previous lecture series of network analysis, so in this session we are going to solve a typical problem using nodal analysis. Okay, so this is a typical problem that is given to calculate the nodal voltages. Already they were represented V1, V2, V3, V4, and the node V5 is grounded. That is also given. Okay, so you need to calculate V1, V2, V3, V4 using nodal analysis, and you need to calculate the Vx, that is the voltage drop across the 2 ohm resistor. Okay, so that is the thing what you need to calculate now. So before going ahead, as usual, the same procedure. First of all, usually you need to identify the nodes. However, all the nodes are given, no need to identify. But you try to understand which are reference nodes and which are non-reference nodes. But in this problem, so V1, V2, V3, V4 are non-reference nodes. V5 reference node. Now you try to understand whether it is a case 1 problem or case 2 problem, a case 3 problem. So however, you don't have here a dependent source, it is not a case 2 problem. So now you try to understand whether it is a case 1 or case 3. If you clearly observe, the voltage source 4 volts is connected between two non-reference nodes. That means voltage source 4 volts connected between two non-reference nodes. So hence I can say this concept is supernode concept, because you cannot apply Ohm's law in that branch. Okay, simple. So because you have a voltage source there. Now even the problem is looking something typical, but we'll go with the standard procedure what we know, what I have explained in the previous lectures of videos. The standard procedures we will try to go ahead. Okay, so now once the indication of nodal voltages are done, we'll try to go ahead to fix the branch currents. So I will try to fix the branch currents now. So I'll try to fix this current as I1, and I'll try to fix this current as I2, and at node V2, okay, so you have a 4 volts battery. So can I take this current in this loop as I3? So it is not required to take that current actually. So because you cannot apply, so what I say, Ohm's law there. Okay, so that is why it is not required to take that. Okay, now going ahead, you can take this as I3, this as I4, okay, and this as I5, okay. Next, this as I6, and lastly this as, can I take it as I7? Not required, because you have a current source there, right? So whatever happens in the circuit, the current produced by the independent source is always fixed, that is 2 ampere. So why to headache with this one more unknown? So take that advantage of current source, okay, and then simply consider this as 2 amperes. Okay, so from this concept, so we'll try to go ahead in applying the KCLs at the nodes. Okay, so try to apply the KCL at node 1. So KCL at node 1. So what are the currents coming in? I2 is coming in, I3 is leaving, I4 is leaving the node V1. So that means I2 is coming in is equal to I3 plus I4. From this, what is I2? I2 is starting from node V2 and ending at V1. So that is why I2 value is V2 minus V1 divided by 2 ohms. Applying the Ohm's law. Okay, is equal to I3. How can you write I3? V1 minus V3 divided by 1. Resistor is 1. Similarly, I4 is through 4 ohms na. So that is V1 minus V4 divided by 4. So this is equation 1. However, you can rearrange this, no issues. So going ahead, is it possible to apply KCL at node 2, V2? So at V2, KCL is not possible. Okay, because you have a voltage source there. Now, because you cannot apply the Ohm's law, right? Simple. So now V3 KCL is once again not possible. Not only on the right side of 4 volts, left side of 4 volts, right side of the 4 volts node also, it is not possible to apply KCL. Okay, so now KCL for V4. Yes, grantedly you can apply for it. Okay, that means entering current are I4 and I5 and 2 also entering. All the currents are entering at fourth node. That means I4 plus I5, okay, then 2 equal to 0. So which implies, so the value of I4 is nothing but V1 minus V4 divided by 4 plus I5 V3 minus, okay, so on the right side you are having what? Left side it is V3, right side you are having 2 volts potential, and then you are having V4. So this value is 2 plus V4 divided by the resistance is 4 ohms plus 2 equal to 0. This is equation 2. Okay, so now applying KCL, however, the fifth node, so it is a ground node, it is not possible. Now, so let me check the KCLs. How many KCLs we have done till now? We have done only 2 KCLs, right? But how many unknowns are there? There are 4 unknowns are there. Okay, now one simple logic is that, so this is V2 and this is V3. So from this concept, directly I think I can write V2 minus V3 is equal to 4 volts. This is the third equation. That means whenever a voltage source is connected between two non-reference nodes, directly you can take the advantage of it and directly represent it in terms of the nodal voltages. I think the same thing we have done in the mesh analysis. Whenever there was a current source, we have represented that current source value in terms of the loop currents, I1, I2, something like that. Can you remember? I think, right? So in the same way, here also you take the advantage of the voltage source which is connected between the two non-reference nodes and you try to represent that value in terms of V2 and V3. So that is how directly I can write V2 minus V3 equal to 4. Now the number of equations are how many? 3. Number of unknowns are 4. Now still you need to investigate the fourth equation. So in the investigation of the fourth equation, so whenever the voltage source is connected between two non-reference nodes, as I said, it is a supernode concept. So supernode concept means what you have to do, you should assume that the 4 volts is removed and then the two nodes V2 and V3 are tied together and making as a supernode combination, and then apply KCL at that supernode. That means sum of entering currents is equal to the sum of leaving currents. This is how you need to apply the supernode. So I will try to make like this. This is V2 and V3 tying together by removing the 4 volts. Now in this direction you have 2 ohms. In this direction you have 1 ohm. Okay, and this end voltage is 0 volts. This voltage is V2 and this voltage is V1. Okay, so in the same way, this way it is V1 and this is connected here 1 ohm, and this way it is 2 ohm. So this is connected to ground. Now also indicate the currents because you need to apply KCL, right? So indicating the currents. So this way it is I2. Okay, so this way it is I1 and this way it is I3. This way it is I6. Okay, so that means what I have done? So the V2 and V3, I have removed the voltage source and then I have tied together the V2 and V3, making it as a super node now, and understanding the amount of total net current that is entering the super node and the total amount of net current that is leaving the super node. Okay, so that is the thing what I am doing now. So that means applying the KCL at the super node. So applying KCL at super node of V2 comma V3. Okay, then what are the entering currents? So I3 is entering, only I3 is entering. Think all are leaving, right? So that means I1 is leaving, I2 is leaving, and then I6 is leaving. So now you'll try to apply the Ohm's law on I3. So I3 value is exactly equal to V1 minus V3 divided by 1. Okay, is equal to, what is I1 now? V2 minus V5 is 0, however, 1, plus what is I2 now? V2 minus V1 by 2, plus I6 is V3 minus 0 by 2. This is equation number 4. Okay, in the super node concept, nothing I have done. I have removed that voltage source and I have tied the two nodal voltages together, or the two nodes together, make it as a super node, and write the KCL at the combination of 2 and 3. Okay, V2 and V3, that is entering current is equal to leaving currents. Only I3 is entering, all I2, I1 and I6 are leaving. The same concept I have applied here, and finally applying the Ohm's law, I got the fourth equation. So now number of equations are 4 and the number of unknowns are 4. So you can solve for V1, V2, V3 and V4. So if you solve for them, so you will be getting the values of V1, V2, V3 and V4 as the value of V1 is exactly equal to 0.3 volts, and then the value of V2 equal to 2.6, and V3 is minus 1.3 volts, and V4 is equal to 2.5 volts. Okay, now in the question he is asking one more parameter, that is what we call it as Vx. Okay, so coming back to that Vx finally now. So we try to redraw the circuit at Vx separately. So it is a 2 ohms. So this is plus minus Vx. Okay, this voltage is how much? V3. This voltage is 0 volts. Now see here, the same picture. So I can understand like this. This is 2 volts. This voltage is Vx. Okay, so now I try to extend this something like this, and here plus minus this voltage across this is how much? V3, because this is grounded 0 volts. So on this observation directly I can write the value of Vx is directly equal to V3. So V3, which is equal to minus 1.3 volts. Okay, so that is how you should be able to understand that whenever he is asking the value of Vx or Ix, you try to take that out. Okay, draw separately and try to understand the concept. Then you can apply the network's logics to get the values of Vx. Okay, so in this way, so you can apply the supernode concept whenever the number of equations are less than the number of variables. Okay, so with this students, so I am concluding. So we have done lot of analysis on the networks on all the basics, that is the voltage division, current division, okay, KVLs, KCLs and star to delta transformations, and then mesh analysis and all the three cases, case 1, case 2, case 3, and the nodal analysis, all the cases, case 1, case 2, case 3. Okay, so everywhere always the important thing what I usually say to the students is always the methods are most important, not the problems. So try to concentrate on the methods, how we are understanding the methods and how we are applying the methods. So once you understand that perfectly, then you can solve any network problem accurately. Okay, so with this, I'm concluding these sessions. So if you really enjoyed the complete lecture series on the basics of network analysis, just like them and subscribe them, and you can comment also too, so that it can motivate us to do lot of videos. So thank you for giving this opportunity. This is signing off, Dr. E. Vijaya Babu.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.